Okay, so the user guide for AWS can be found by Googling AWS user guide, which will take you to this URL. It changes frequently. AWS has grown very fast and continues to expand. So it's pretty hard to sort of say, well, I'm going to cover everything. There's no way. I will show you, like they already have, I don't know, 70 products or whatever on AWS, right? We're not going to even touch all of them. We're going to show you some very basic stuff to get you through. So I'm going to start with a little bit of what is cloud computing, talk about some of the benefits of using AWS, especially for your research, and then look a little bit at sort of what we might call the web services stack. What is the series of things you can run and get access to? So the basics of cloud computing, you'll hear this term a lot. And really, there are three primary areas that people call cloud computing: software as a service, platform as a service, and infrastructure as a service. And I've highlighted the bottom one because for your research, unless your research is about software as a service or platform as a service, the bottom is why I think you will find Amazon AWS useful, because it is your low-cost, large-scale research infrastructure. Right? Now, if you really want to run web services or do software as a service as a company or as a product, the first one's really important. Or platform as a service for doing toolkits and whatever, all that stuff is very important. But that's more important at the business level. For your research, it is unlikely you can use software as a service as a huge part of your research. Why? Because it's already out there. It's not novel. It's not new. But there might be some things you can study about it that would be new. So I'm not saying it's not there. So one way of thinking about cloud computing is it's a scalable hardware layer. If I need one computer, I've got one computer. If I need 20, I get 20. If I need 100, I get 100. But on top of that, if I just view it in terms of hardware, it's a little bit more limited, because beyond the hardware, there are some very basic services for what we may call the grid service, the storage service, and the queue service that structure how I get data in and out. So right, it's not just how many computers I have, but how much storage is there? How fast can I get to that storage? What can I send where? Which the grid service is sort of communication. And then a queuing service that might let me actually manage large flows of information without knowing how large those flows of information are. So if I'm running an experiment and the output of one stage goes into another, the queue in between has to be big enough to hold everything. And if I know what my research is, that might be fine. If I don't, I need a queuing service to actually handle lots of things. The queue depends on how fast the computers run. So if this stage can produce data really fast and this stage consumes it much more slowly, then my queue will keep growing. And if I don't have good infrastructure, then I have to worry about the sort of natural queue. What do you guys do for a queue? Anyone know what almost everyone does for a queue when they don't think of it as a queue? Nah, that's actually looking at it as a queue. We call it the file system, right? The first stage of research writes a bunch of files, and the next stage of research reads a bunch of files. Okay, I/O, disk I/O, 10,000 to 100,000 times slower than memory transfers. So if you do it that way and you write your experiment where the first thing you're going to do is you're going to write it to disk and then you read it to the next stage, right? You've ensured a slowness in your pipeline, but it guarantees scalability because I can write a terabyte to my disk if I have a big enough disk, and I don't have to worry about what's going on in my stages. So there's some flexibility. So we really want to be able to make our services so that we can automatically do things efficiently and do the queuing and whatever. As I said, there are many close choices of clouds. I'll go through. The biggest by far is Amazon at 34%. Microsoft Azure, you've probably heard of, is 13%. IBM Cloud is 8%. Google is 6%. And Alibaba was 4%. And this was as of March of 2018. Did anyone notice anything about these numbers? They don't add up to 100%. Not only do they not add up to 100%, they don't add up to close to 100%. Okay. Does anyone know there's actually a big provider that's not on this list? Anyone know what that is? These are all the names you probably heard of. Alibaba I just put up there because I think Alibaba's down there, but it's a new one, but it's not. So, anyone have any idea what the other cloud providers are? Okay. So the other cloud providers, so the next biggest, in fact, the second largest cloud provider is a company called Next20. Okay? And you've never heard of them because they have, I'm not sure what the total number is, but they used to have like 40 clients. Now they probably have 80 clients, right? They only do cloud providing to really big people, right? They have no customer-facing stuff. It's all B2B, and they go after, like, Dell, right, is using cloud services from Next 20. Now, they also use a little Amazon Web Services, but they get a lot of their stuff from Next 20 because Next 20 is largely dedicated, as lots of the other ISPs. So people like Comcast uses Next 20 as well, right? They have this dedicated service where it is cloud, but it's not public-facing cloud. It's very focused on what they're going to do, and they're sort of a big chunk of their market. So there's a few other providers in this very specialized niche of, we are a cloud, but we're not a cloud for everybody, so you don't hear about them. So you're not their customers. But, services that are offered by these cloud providers, there's really a ton of them. As I said, I think Amazon got more than 70 different services they provide. I believe Amazon is the biggest with the widest range of services. We'll review some of them and how to do that. I use AWS way more often, so I'm just going to use that as an example. But just about everything I'll talk about today, almost all those services exist within Google Cloud as well. Most of them exist within Azure, but I don't have an Azure account that I can get you free access. They gave the company I work with free, but not students. So first, why do you want to use AWS/the cloud for your research? First, you have a wide range of hardware to match your research needs. Your lab, your faculty's lab here may or may not have stuff that you want. Even if they have everything you want, it may not be as easy for you to use. There are many pre-configured machine images to choose from. So if I want a machine with TensorFlow installed, it might actually be easier to just go to Google Cloud or to AWS and say, give me a machine with a machine learning instance already configured with with TensorFlow and Docker images and stuff, and I don't have to worry about installing everything. If you do it yourself and you own your own machine, great, you can learn how to do all that installation stuff. If you want to learn how to do all the installation stuff, you can also do that on AWS because you get full root access to your VM. That's good and bad. You can destroy things if you want. It's your machine. You can't destroy Amazon's cloud, but you can completely remove your file system if you want. If you haven't figured out how to lock yourself out of your AWS instance yet, I can easily show you how to do it. I've done it multiple times by setting up firewall rules that don't let you reach the internet anymore, in which case your unit stops talking to itself or to anyone else, right? You basically say, only local communication. Then how did my SSH work? You get free accounts. So if you sign up, which I sent email about, just make sure you had the links, which I'll mention in class as well. You get $100 worth of credits for free, maybe $150, depending on exactly when you signed up this semester. And I can get you more in the future for your research. You can probably get another 100 outside of this class if we do it. If you're doing it right. Your advisor can also, or you can write a proposal to Amazon to get free. Faculty research grants are like $80,000, $40,000 worth of credits. They're pretty hard to get, but getting $1,000 for your research, every student I know who's asked for that normally ends up being able to get their advisor to get that. Campus actually has some ways of getting you some extra Amazon credits because if you don't know it, we actually buy, Campus pays for a lot of Amazon stuff, like all of our web services now are running on Amazon and things like that. So if you do actually use it for pay, you pay per use. You're only charged for the disk space, CPU, and bandwidth that you use. From a company point of view, that was very useful. Sorry, I got to take my head off here. It's too hot. So you don't have to pay as much. So for some of the projects, we actually paid a small amount. For one of my students recently went over the $100 we needed for their work, but that's okay. It was like $140, so I paid $40. We still got our work done. It's pretty easy to scale. Abhi, one of my previous students, did a large chunk of the last year of his thesis on it, in part because, I'll come back to some other reasons, but the CPU and bandwidth limitations, like we paid like $70 for all the work he did. In terms of the amount of time it would have taken him to set stuff up, coming back to this pre-configured machines and stuff, right? It would have cost more than $70 worth of his time to set up all the machines, right? So cost is actually, I don't care if you have to pay for it, if it's also saving money someplace else. But the other reason the student did it was actually the instant scalability. After doing some very simple processing locally, it was easy to scale up and use 50 machines, which is a little harder in my lab, although I have 50 machines, they're heterogeneous. So it's not easy to say, go make it run on all 50. There's 50 different machines, you configure them, you'd waste a lot of time. So it was pretty easy to scale stuff. Another one of my students did his work on AWS, and actually it had to be on the cloud because you're measuring cloud performance and whatever. So it's very easy to scale various things, and I'll talk a little bit about how to do some of that. Very high reliability with infrequent outages, at least so far. The data is redundant in the cloud, so if Amazon East even has a problem, you can just move to Amazon West, and you generally don't have to worry too much about anything going on. Their reliability is measured in multiple nines, like 99.9995% uptime or whatever. It can vary a lot, but your internet access to them is probably way more unreliable than their internet access or their reliability. All the services have some levels of built-in security. So one of the other nice things is their images, when you spin up one of their images, when you first spin it up, you can be pretty sure it has all of the patches and things applied to it. The default for most of their images, in fact, they're all set up to auto-update for security. You can disable it because sometimes updating security patches break your work and you don't want that to happen, in which case then the security stops getting applied. But they at least start with built-in security, and most of the services have pretty good security built into them. There are API libraries available in all major languages, which includes what you might not consider major languages, things like R, Go. There's stuff for all those. So in whatever language you're starting in, there's a pretty minimal learning curve. Some features are naturally more suited towards some languages. So there actually is a C interface to a whole bunch of stuff, but it's really painful to do like JSON parsing in C. So that's the JavaScript object notation. So you got to balance out what you're going to do. One of the reasons I like Amazon, first of all, is because it's the first one I learned. They've been doing it for about 15 years. They also have many customers, so it's actually a saleable skill. As I mentioned, my student did one last part of his thesis. He wanted to have the skill of having done it on AWS. He could have done it in my lab. Might have been slightly cheaper, might have been more expensive depending on his time. But either way, now when he graduated, he could say, I did this part of my thesis in AWS. I've done this and this and this. So when you go to look for an industry job, that skill might actually be a saleable thing you want to get for an internship or for a job. So in that reason, it's worth doing a little bit of that just so you can sort of say you know it. The bad thing is things change very fast. If you were really good at AWS 4 years ago, a number of things have changed. Lots of it's still the same, but a number of things have changed, so you're going to have to keep staying up. So I'm going to very briefly talk about 4 core elements that I think you might use in your research. There's a whole lot more I will briefly touch on. So what I will call Amazon Web Services stack. The first 2, I can't imagine you doing research on AWS without them. The Elastic Cloud Service, EC2, and the Simple Storage Service, S3. This is pretty much where you compute and where you store. If you're going to use EC2, you probably have to use S3. There's a few other things you could do, but you really wouldn't want to from a price point of view. The other 2 are very simple things, but if you need to do very simple database services, because you have lots of data and you want to make it efficiently accessed, the Simple Database Service is very easy to use, and the Simple Queue Service, which is a way of sort of queuing up data between things, can also be very easy. So these are the 4 that my students have used that are pretty the easiest. So EC2, the Elastic Compute Cloud, is a sort of on-demand grid of computers. They basically have this idea of there's a bunch of machine images. By a machine image, we mean that it's really a virtual machine that's running an operating system and some apps. So you basically, to use this, you create a machine image, you deploy the image to S3, once it's deployed, you can then start it up. So you're going to start one or more regular instances, and then you SSH into it and you use it as a regular machine. Or once it's started up, there's web services and you connect to it through web services port, whatever you set it up to do. So the main options that you have in this are whether or not you're going to have dynamic or static IPs. There's a price differentiation. How many cores you're going to want to have, where you want it to run. Do you want it to run in North America's east, west? You want it to run in Singapore? You want it to run in Europe? And what kind of persistence you're going to have in terms of the Elastic backing store, where you're going to store your data. So some very simple examples for your EC2, sort of batch processing. If you want to run an experiment that, say, needs a lot of memory, right, and you want to run 10 or 12 versions of this, okay, so in my lab, I have one machine with more than 256 gigs of RAM. I have one. So if my students want to run 3 or 4 experiments that need 300 gigs of RAM each, or 380 gigs of RAM each, you can't run them all, so then you have to run them sequentially. But I can go to EC2 and I can rent or buy a machine that has 384 gigs of RAM, which is actually, I think, the biggest you can get right now. But I can have 10 of them. So I could set up a machine and basically have it run the same code on slightly different data with a different parameter, and then all of them, I could run 10 machines at once. So you get them all configured, you get them running, and then you basically spawn off instances, and based on some parameter, they will run themselves. It's another variation of that is where you run them on subsets of the data. So it's not memory limited, but I want to run a bunch of stuff in parallel. I break my data up into 10 giant chunks, and I run in 10 processors. I break it up into 50 chunks, I can run in 50 processors. And the difference between 1 and 50 is literally what number I type in a box and I say run. That's especially true if I've structured my code right. So there's a little bit of effort there where the machine has to know what is this instance number, and therefore what range of the data it works on. But if I know I'm going to have 50 instances and I tell everyone, take your instance number, which is one of the parameters you can get with a function call, and then you work on the ith out of 50 chunks, then you know what it is. Another very common way is if you do everything with random data, then it doesn't matter. Then every instance is the same. You go to a random subset of data, go do something. And it's common in machine learning to do a bunch of random runs, so that becomes very easy to do. The partitions that separate the data are stored in a configuration file to sort of say, this instance has this partition of the data and do things. If I'm actually doing things that need web services, so I'm looking at anything where I'm going to have like REST APIs or whatever, all the instances are configured with sort of the same code, and then I can do more instances can load as I need load balancing. So from a company point of view, if I want to do web services, I can automatically scale. If I hit this load, spin up a new machine. When it hits a new load, spin up this machine. Oh, look, the loads are small enough, kill a machine, right? Because they're storing all their shared state in either the storage cloud or the database. It doesn't matter if machines go up or down. And so that gives you true scalability. So you can do some of that for your experiments. If you make your experiments some mix of web and batch processing, so web services control what gets fired up, then you can do sort of a mix where the web services fire up some compute code that happens and then puts all your results together. So those are all very simple. If I do it with web services, the DNS servers automatically distribute requests between the load balancers, so that literally if I ask for www.uccs.edu, that actually gets rerouted into Amazon, and it's one of n machines where n depends on how many people are hitting www.uccs.edu. So as the load goes up, if a bunch of people start trying to do registration, there are more web service instances needed, then there will be more servers at Amazon, and when you ask DNS, what does www.uccs.edu mean, it will give you different answers depending on who you are and what the current loads are. So it dynamically changes the name to number mapping to make all that stuff transparent to the end user. So it makes it pretty easy to scale stuff up using that kind of model if you really are doing it. May not be relevant for your research. The first is, I think, more common on my side of the research, but who knows where your research will go. So underlying dealing with this for almost all of them is I have to have somewhere to store my data, especially if they're running in parallel where I don't control where they are. You don't want to really think of this as one giant file system. It's not really a file system. It's more generic than that. Simple storage allows us to store large media and everything else. But it was really designed for storing larger blocks of data, not just really small items. So if you think of it as a file system, think of it as a file system with a very large block size. And the reason it's that is because it actually wants to transfer blocks between the storage servers and the compute servers in large blocks. So it will do them in this sort of function. So instead of a file system with names, everything is based on unique keys, which is like a hash of stuff. And I do puts and gets into buckets based on unique keys, and buckets, or think of those as folders. So if I think of a folder plus file extension, the bucket is the name of the folder and the unique key within it. The unique keys are actually unique across buckets. They're supposed to be unique across all buckets, so it doesn't matter as much. It has both private and public access and groups, so you can do the sort of storage permissions you're used to. And it has support for very large objects. One of the reasons one of the companies I've worked with uses it is because we have this unfortunate limit of a 2 terabyte file, and their files were bigger than 2 terabytes on a regular basis. It made it much easier for them to not just store them in S3 because they can have it as one big file, but to then do the processing in the Elastic Cloud where they could break these giant files up into pieces. But if the file is sort of a streaming file, you can imagine video things, which is the space we work in. Video files can get very large very fast, and S3 allows you to keep appending to an object, right? So not only do I get the object, I get a handle to it, I can keep appending to it, so I can add to the back end of a streaming file while somebody else is already reading off the front, which approaches the queue stuff we'll talk about and it becomes related. Image video storage on S3. Once you put your media up there, S3 will serve it, which is common for content distribution. This is also common for people trying to make it so that my data is replicated. S3 will transparently speed up access to your data based on where it's getting accessed a lot. So they literally do the equivalent of prefetching for you so that they get the services. If they're going to ship one block from here to Tanzania, and the first block they ship, that's it, ship a block. You ask for the next block in order. Not only do they ship the next block, they ship the one after that. They start prefetching because it's to their advantage to maximize their bandwidth during transport, and they expect now you're going to use it. Just like any OS does prefetching for reads, they start doing some of that as well. So that can make it pretty interesting. You actually only pay if you read it. If they prefetch a block and you never touch it, you don't pay for it. But reads are 10 times cheaper than writes, so you can do a lot of reading for each write. You can also use them to serialize your Java objects. They have a defined keys, which makes it easy to deal with them in and out of S3. If you're dealing with small Java objects, it's important you actually think about how many objects fit in a bucket and do the right bucketing structure. Otherwise, you're a little bit inefficient because it'll spread them out across buckets, which means you don't get the prefetch reads because prefetches are based on their buckets, right? So you might want to think about how to serialize them inside of that to get a little bit more efficient, but read them back when you want. While I'm not going to have any slides on it, Amazon has another storage, actually it's 2 other levels of storage, but it has a level of storage called Glacier, right? And as its name implies, it's glacially slow. It is super big and very cheap as long as you never read from it. Writing to it is very cheap, and the expected read time is 7 days. So if I want something, it may be 3 to 7 days before I get it. I think 3 to 7 is where this is. So 7 is, I guess, the maximum. And there's probably, I think there's 2 pricing tiers, but for what we used it for at my company, Glacier was our critical offsite backup. We hoped to never use it, but when we shipped software, we wanted to make sure no matter what happens. So we had an offsite backup, but who knows, right? Maybe that goes too. This was partially paranoid after my partner's house literally burned down in the fires, right? And that was our offsite storage. It's like, wow. And cinders were falling on our company's office building. It's like, wow, we could have lost everything this week. Let's have one other backup way offsite. And so we used Amazon Glacier, which you just write stuff to, and if you never read from it, it's very cheap. And if you read from it, you pay a reasonable price. So that was our sort of offline extra backup. And if I had really big objects, I might think about that again, but I don't have stuff I financially depend on in my lab as much. So. Simple Database Service is a very basic database and indexing service. In fact, I would not quite really call it a database, but that's what they call it. I would just view this as a giant key value pair, right? Which is really not a database in my view, but it's okay. So you have a key and some attributes. It creates flat file databases with auto-indexed tables. Okay, you can't do things like table inversion and you can't do relational joins or any of this other stuff, but it's pretty simple. And if you notice, right, it's based on some flat tables with keys, which is what their storage is. So this really is just a quicker way of getting through your data. One common way of doing this is to associate your file names with your keys. Right? So you had a file name you wanted to put in Amazon, but the only thing you actually get to use for putting and getting are keys. So if I want to actually remember something by file name, what do? Well, I put it in the simple database where the index media is stored on S3. I have the same key, and here I have all the metadata attributes. So if I want to be able to look something up by its name or any of its other metadata, I would do that. And I can also use it as storage for non-nested data. So if I really have a bunch of flat files, things that might be small and therefore I don't want to actually use S3 for them, I can use them in the SimpleDB. I thought I had slides on SimpleQ. I guess I don't. Because, well, maybe I do after this. But so Amazon has a whole lot of other features. So I've touched on a few of them here. But inside of compute, besides EC2, there's EMR. It's elastic matching. EMR, elastic match reduce. MAPREDUCE, which actually I'll talk about a little bit. Amazon Virtual Private Cloud, Amazon Kineticus, Route 53, Direct Connect. All of these are specialized compute services. Most of them are for web service-oriented things at company level, but they all provide some level compute storage. Besides S3 and Glacier, which I mentioned, there's CloudFront, which actually I use all the time. CloudFront, if you run web services and you run websites, CloudFront is depending on who your service provider is, a very cheap or maybe even free content delivery network that will speed up your website. By basically using Amazon's web services, you get this CloudFront that will cache your website, and when people ask it, they play games in DNS space so that instead of your DNS going to your machine, it first goes to their machine that says, is it my local cache? And if it is, deliver it, otherwise go here. And if you deal with a global distribution or just lots of people hitting you, you'd want to use that. So when I do web stuff or apps for conferences where we'll have nothing happening on this website for weeks, and then for 2 weeks, 3,000 people hit the heck out of it because it is their conference app and they do everything through it. And those kinds of things, you really need to have that content distribution network, especially because if it's in Europe, right? I don't want my servers here sending everything back and forth across the pond. That happens naturally with CloudFront. They have a bunch of database things. So in addition to the Elastic Cache, which I didn't mention, they have this thing called Redshift. I've actually never used it. RDS and Dynamo. So I think Redshift is their NoSQL Mongo type structure. I'm not sure. One of these two is, and the other is a relational database. RDS has got to be relational database services. They have a bunch of application services for making any of your app stuff go faster. So they have things to speed up search. They have things to do transcoding. So if I want to have video of one kind in and video of another kind go out, they'll do that for you automatically, which is where those very big files from one of the people I worked with goes from. They wanted to take in raw, compressed files, which stream in at huge sizes, and then transcode them to actually 6 different transcoding speeds. So if you think about streaming from like a 4K video sensor, right, streaming at 30 frames per second, and then having it come out at HD, whatever, when you do YouTube, right, you get a little pull-down menu with different sizes. Somebody's got to do all that transcoding. Google does it for YouTube, but you want to do it yourself, you get to do that with Elastic Transcoder. And then there's a whole bunch of deployment things for doing Beanstalk for web stuff, CloudWatch, identity management, a number of other items at the top level. And this is only about half their services. So AWS has a ton of things. If you're really a business trying to build on top of stuff, there's a ton of things to make it go fast. So first things, which is related to your assignment. So I'm going to make the assignment a little bit more general. I'm basically going to ask for you to show me by recording your screen, because that's the easiest way. I was trying to figure out before, how am I going to know if you actually go through all this? I want to know that you can spin up a machine, log in, run some code, right, and get some results. Okay, so I'm gonna and I'll write this all up tonight or tomorrow. But basically, you're gonna log in, get to the point where you can create an instance on AWS or Google Cloud, log into the instance, run code in whatever language you want, showing me you ran some code on some data, and then get the resulting data back off of it to your machine. And the easiest way for you to show me that you can do all that is actually to do a screen recording. I will also post instructions on how to do a screen recording. Is anyone here using something other than Linux, Mac, or Windows? Anyone? So yeah, I'm pretty sure. So anyone running on Linux? Okay, so I'll make sure I do all three for how to screen record in any of those, just to make sure it's straightforward. Anyone not know how to screen record? Okay. Screen record, video. I want a video file. So how many don't know how to do a video? Okay, fine, then I'll make sure I post instructions. Okay, and by the way, I do screen recording for every class and been posting them just in case you haven't noticed that. But so let's start with firing up instances. So I'm actually going to start with this link because I have to do this. I forgot to start up today in split screen mode, so let's go do, yeah. We don't have enough accounts that they give us a full console, but I can see, and sometimes, so it'll say like these were ones that were just rejected. Somebody tried to sign up with a Gmail, right? It's just rejected. Other times it sends me mail, and I've never figured out why or how to get it to do it. And maybe it's when they get rejected, there's something for them to go in and do something. I don't really know. But most of them get, I see Ahmed already submitted one this week, right? Maybe today, 10/29. It generally takes a day or two to get approved, and then it'll be active. So even if you know what you're doing, you might want the extra $100 of free time to go play with. Go ahead and do it. If it gets you, if you get an error message back, send it to me and I'll see what I can do. But if you use UCCS as your email and you pull down from the menu, it should work fine. Most people. So Ahmed, you had no problems, right? So. So you want the starter account? Okay. Yeah. So, I mean, oddly enough, if you already have an account, right, and you go through this, I think we'll add some free credits to your account. But if you don't already have an account, then say create one. So that's basically how you sign up. That will take a day generally for you to sign up. You're then going to create a user, which is your username inside of that. I actually think when you do the educate one as a student, it automatically creates your username and tells it to you, right? So I'm not sure you have to do anything special for that. You're going to create a key pair. So I'm going to go ahead and click on it. To create the key pair, I'm going to sign into my console. It tells you to sign into your console, right? So I'm going to go ahead and sign in. So when I sign in, it actually takes me to a page where there's things like launch a virtual console, connect to a device. These are actually other things that will send you through a more focused tutorial for just this one piece. So I think if I already have key pairs, so if I go to my account, or maybe it's my security credentials. No, not there. So when I look down here in my access keys, so this is one of my access keys, right? And I can create new ones. So I just click on this button, create new access key, and it'll give me a key. And it basically gives me a key pair. I can download my share of this. And then when I go to do SSH, I use SSH with a key to allow me to get back and forth, right? So I add it to my key ring. Key ring depends on what your OS is. So Mac is different than Windows, different than Linux. But it's pretty straightforward in their documentation. So they go back. Right? They'll actually tell you after you've created it, you go to your console, you create the key pair, save your key pair, and if you're using SSH on Linux or Mac to connect, you use a particular command, and it goes through those. Right? And there's, of course, lots of interactions. Your AWS instance can be running Linux or Windows. Can be going in from Linux or Windows or Mac. Right? So you have to find all possible combinations, but this will walk you through what that is. And if you try following these instructions and you get really confused, you can ask me a question, but this should be, you're a PhD student in computer science, you should be able to figure out SSH. But some people get annoyed because you have to do it with this key stuff, and you have to do it with the key stuff. So that's, you may not have done that before. Once I've done that, if I want to create a virtual private cloud, you only do that if your research is on cloud. You got to work with that. So if you're going to work with multiple people, you can set up security groups, and that will allow you to have all of those items. So now I'm going to go back. So after that, you should have your. Actually, I want to go back into the console. After you've gone through setting all that stuff up, you do not have to videotape setting all this stuff up. Okay. You just want to videotape actually firing up your instance. Come on, sign in. No, you can. Depends on. So if you're going to use multiple machines in a cluster, yes. If you're not, no. Depends on what you're trying to do with it. So after you've got your user account and everything set up, you've got your keys, you can then just go in here, and for this assignment, you can really just talk about launching a virtual instance. It's going to put up the dashboard for my instances. I have no idea what it's going to remember. So I can then choose what kind of machine I'm looking for. I'll come back to making machine choices in just a little bit. So I can, go for an Ubuntu server 14.4. You'll notice these are free tier. If they say free tier eligible, even as not a student account, you're actually not in the free tier. You have a student account which gives you paid tier access. But things that are free tier eligible, when you first try and sign up, and with any random email, you can always make another account. They know it happens, but they don't care if you're just doing small amounts. You can get this free tier and do some small demos of stuff. So then you would choose whichever server you want. If you want to run something on Microsoft Windows Server, this is not free, but you can always run something if you don't happen to have a server laying around. That's okay. So you would choose your server. I will go for Ubuntu. Okay. Now it's going to ask me what size machine I want. One virtual CPU with 1 gig of memory, or do I want 96 CPUs with 384 gigs of memory, right? I can choose either of those. They're not all free. They're not all the same price. I'll look at pricing in just a second. But you can figure out what you're going to do. So they're telling you some of the key characteristics. How much memory do you get? How much storage? What storage choices do you have? You'll see some of these have elastic backing store, which is your local storage. Others have dedicated SSDs, which really speed up local storage if you're doing experiments. What kind of network performance you have. Some low to moderate, and then 10 gigs. So it depends where you're going to go with it, and whether or not the machines support IPv6. Most of them do, if I'm running any of the Linux instances at least. I can actually also ask for even older machines. Not particularly common to want to do that, but if you're going to do spot pricing and you really don't care, that's actually a very useful thing to look at the older generations, because most people don't like the old generation, so those machines run unused more often, which means if you're paying for it, or if you're trying to figure out, maximize how much work you can get for the fixed free dollars you have in your free student account, the old machines often run longer for cheaper, because no one wants to use all the old ones, right? If you're paying for it, why am I using these old pieces? Except that they want to use the old stuff for it being cheap. So I'm not going to go through all this. So I'm just going to go ahead and I'll keep moving forward. I'll say, so now if I'm ready and everything's configured, I can actually review and launch. Click down here. Otherwise, I can click on configure instance details. Now I can say how many instances I want. I can request spot instances. And so for this particular machine, the current pricing for spot instances are 0.0035 cents, so 0.35 cents per hour, right? So with a $100 limit, you could run this for quite a long time. I can also set a maximum price. Spot prices actually go up and down depending on what people are using. So they might go up, they might go down. I can actually have my persistent, I can set it up whether or not I want it if it gets killed off, especially in spot instances. If there's no machines available at that price, your process will be suspended. You can either have it stop, or which terminate or stop, and if you pay extra, you can make it hibernate, but you have to first configure an instance that can be hibernated. This one isn't. There can be all kinds of time zones, so I can go in and say ranges of time when to start it, how long it's valid. I can set up subnet preferences. I can set up whether or not it's going to get an externally available IP address and what you want to do with it, and so on. There's a whole bunch of items you can play in here. What you do in terms of how it's going to monitor people, and then some configurations. I strongly recommend you use this user data field if you have more than one instance, because after a little while, you will start forgetting them. And when you see instances in your box, they have this wonderful long hashed string number, right? So this useful data helps you understand what it is when you want to label them. So next I can add tags, which I guess maybe is the thing I was thinking about, not necessarily the comment. So add storage, how much storage do I want to have, what do I want to pay for it. Add tags, maybe this is where, this is where I tag them to give them names so I can look through them if you have a bunch running. Put it in a security group. What am I going to do? What port ranges? If I want to have where they can go, if you want added security, you can literally say the only people who can get to this machine have to come from this IP address. It's common for us to do things where we would do this. Custom, where I would do 128.198. Well, for my lab, 147.0/24. This lets it go anywhere from my lab, or I could do anywhere on campus. Right? And if you're not really sure about security, this will add a lot of security to what you're doing, because no one else in the internet can attack your machine. You can only get to it if you're coming from campus. And you can VPN into campus to then get to your machine. So you can always get there, and you'll limit how much security you have to worry about with everyone else. It's not a panacea, but it's way better than just saying, sure, let everyone attack my machine. And you can have multiple ports, so you can have SSH access. You can set up all kinds of other ports and use this as a place to set up ports inside of it. At this level, you really can't shoot yourself in the foot. You can just open up ports. And now it's going to ask me to review and launch. Right? So it's going to tell me all these things. And then I click on the button launch, and the machine will be there, and I can SSH in. I'm not going to go through that now, but that gives you an idea of what does it take to set up and launch. You'll have to have your own keys and then SSH in to do stuff. And then you'll have to upload code /data, get something to run, and come back. Any questions on that part so far? Again, this is all pretty simple. In fact, even though I wanted to do some of this in class just to make sure everyone saw it, there are way better tutorials online. So if this didn't get enough detail, just look for a tutorial on how do I set up an AWS instance and how to get data on and off, all that stuff. So the next thing I wanted to go to, Amazon has a bunch of documentation, so I'm just going to go to some of those. Okay, so API and reference guide. So the link is in the website, but this is really the documentation. There's tons of documentation on pretty much any one of their tools. You can go through all of that, see where it goes. I thought one of these was pricing, but maybe that's in another link. I'll just do... so this is pricing history. I didn't want hit pricing, I wanted current stuff. Although history can be useful because you can look back and you can sort of say, okay, here's what they were paying at different times of the day. Right now you only get to see what's going on right now per hour. So this is the machine I was just on, so 0.0035 per hour is the current spot instance for this. If I wanted that machine, there's actually some cheaper machines, smaller ones. If I wanted that giant machine, so unfortunately here you have to know what the names were, but the machine with 256 gigs of RAM or 380 gigs of RAM is I think the M5, no, it's a 96 large, isn't it? Well, I'm not positive which one it was, but so M is the memory, so it's got to be the one large one. So they're about $1 an hour, right? But if you think about how much it would take for you to upgrade a machine to have enough memory to run something large, that can definitely be worthwhile to make it happen. Noticeable difference between Linux prices and Windows usage prices, but if you want Windows, that comes with licenses for whatever you want. Windows licenses are generally much easier if you don't go to very large number of processors because they're more expensive as you get to high core development. So these are what are called the spot prices. I can have defined duration. So in defined duration for, let's try and get the same machine. The T2 Micro is actually cheaper at 0.006 per hour, but I say I'm going to use it this many hours this part of the day so they can schedule stuff. So you can do things with schedule storage, and then you can do should be on-demand pricing someplace. Where's on-demand? No, so this will give you advice on demand versus spot, but that's not giving me demand prices. So if I go in, let's go over here. On demand is I want it now, and I will pay whatever the going rate is for now. So for that T2 small, it's 2 cents per hour compared to 0.3 cents per hour. Same machine, but if I say I want it now and I want to keep it for as long as I want to use it, I pay extra. So there's a very complicated pricing module if you want to go back and forth between them. There's also this thing called reserve where I have a time window. So all of those are options to play with EC2. For this class, for what you need to do, you can probably just buy with spot instances. It can be very annoying if you do spot instances early in the morning and then other people's web services ramp up and you lose your spot instance. So if you're going to do spot instances, my recommendation is choose the locations in the world that are not about to have their business day ramp up, because that's when you tend to lose your spot. And save your work often if you're working on them. Okay, so I'm going to quickly go through a couple of the higher level services, because one of the things you might end up using, Amazon has a number of things that can actually help accelerate your research besides just having computing. So as I mentioned, they have a number of pre-configured machines. So if you want to use TensorFlow and you don't have it set up, and you don't have enough clout to get it set up the way you want, Amazon's got a whole bunch of machine learning instances and, importantly, machine learning libraries. So their AWS machine learning category, if you go into the help for that, you'll find about a whole bunch of stuff where they talk about their resources. They already have pre-trained ML models, so if I want to do a comparison, I might be able to use one of the pre-trained modules. They have a whole bunch of stuff to help evaluate the quality of your measure, and a whole bunch of things built on top of TensorBoard that you can use as well. So as the easiest way to interface with Amazon's machine learning toolbox is through an iJupyter notebook, so inside of Python, right? So you can interactively work with it. So you can be running inside your notebook here, and the back-end computing is all happening on Amazon Cloud. So it makes it very convenient if you're working in that. If you're more of a C++ kind of guy like me, then you fire up a console, you do all this stuff like that. But they've really made it easy for those trying to do the notebook, because it's hiding inside of your notebook. And then you can literally do stuff where you're going to upload your model, and given the model, you can use, if you're using cloud-based data, you can basically connect the two of them, and it will generate instances and do all of the processing. One of the companies I've been helping is one's using Azure, one's using AWS for their machine learning stuff. And on that side, they literally have it set up so that as more data comes in, it will spin up new instances to say, okay, I have to process more data coming in to do our machine learning instances. And if they get enough data, they train a new model, which is not actually in this drawing. They come back in, but otherwise you can apply your machine learning model to answer questions for your customers directly, or to do security, which is what both the companies I'm helping do. On the other side, before this happens, I can change my computing pipeline, use their code commit pipeline, and basically build it so that it goes back into, in this case, Elastic Compute Reduction engine, which we'll talk about in just a second. So that gives you a very nice way of putting things together. So this is not quite how they're using it, but this was one of Amazon's predefined slides. So if I had some data coming in inventory, I can create an object, and Lambda is their functional evaluation engine that decides whether or not I need to make some changes. And if so, then I can submit a batch job to some level of processing that can then go back out. So if you insert labeled image data, space we work in a lot, you can then take that and then use that for your search results, or use it in one case to go back and relearn new models. Okay, and if I need to, for face stuff and for object recognition, Amazon, like Google now, actually has a recognition engine pre-built with predefined classes that I can use to do certain kinds of computations. So if you need some machine learning to do your work, you might actually be able to just leverage what Amazon's already got built into their recognition engine. It's pretty good. It's not the absolute state of the art, so it's tough to use it as a benchmark comparison, but in a couple of our papers, we've used it as a point of comparison because you're sort of saying, here is what we get if we do this with Amazon recognition, right, as opposed to what our algorithm does. And for many reviewers, if you can do better than Amazon, it sounds pretty good, right? And there are actually many places where if people have done that, they'd have found out they didn't beat Amazon. So sometimes there's an advantage to actually doing that level of comparison. I'm going to finish up Amazon, then we'll take a break. So I'm going to briefly mention two things. These are actually now things that are related to cloud computing. So these are straight up cloud computing tools. But some people might be afraid of doing cloud computing until you see how easy it is to do. So Elastic MapReduce is a web-based interface and a command line tools for running things what are called Hadoop jobs on EC2. And Hadoop jobs, which I'll talk about in just a second, make it really easy to do certain kinds of parallel processing. And in its simplest form, it's really trivial. And in more advanced forms, it actually allows you to do some interesting things. To do this, all your data is stored in S3. The EMR will monitor your job, shut down machines after using them. There's a small extra charge on top of using EC2 pricing, but it's nothing like if I had used 50 machines, taken the time to spin them up by hand and do a bunch of work. So this can make it all pretty simple. And if you really want to have more control over how Hadoop runs, you can run the cluster manually, and then you don't pay the extra charge. The extra charge is really for them to handle all this. So what is MapReduce? It is a very simple data parallel programming model for large-scale processing with large data sets. It allows you to deal with a bunch of cheap computers. Sometimes this can actually be more efficient than trying to deal with a GPU or some of the other things. And I didn't mention that when I was showing you models. But if you need a GPU, you can get GPUs through AWS. So you can do training. Currently, they haven't deployed the newest T1000 or T100 models, but they have the older ones. So I think you can get up to 16 gigs of RAM in your GPU, but not anything larger right now. But, maybe it's just the 8. But so anyhow, MapReduce allows you to do highly distributed processing and it's high availability. So MapReduce was actually pioneered by Google, where it processes currently, well, this is actually a 2-year-old slide, it's probably doing 30 to 40 petabytes of data a day for Google using MapReduce. It is huge inside of what their organization does. It's also really heavily used at places like Amazon, Facebook, Yahoo. Facebook has its own parallel stuff in addition to that, but it's pretty powerful. So at Google, the index construction for Google Search and article clustering for Google News and a bunch of statistical machine translation stuff are all built on top of Hadoop. Right? So they all are running this sort of MapReduce paradigm. And one of the other nice things about it is not only is it highly parallel and scalable, you can actually dynamically scale it based on what resources are available now. And so the index construction might take longer because I needed more machines for news. And I can make those two different processes play off against each other and make it happen. So all of the stuff by doing Yahoo Search and Yahoo spam detection for Yahoo Mail, all of those are also in Hadoop. So Google obviously is not using it on AWS. I don't know if Yahoo's got their own internal for most of it, but Facebook, data mining, ad optimization, spam detection, all that stuff happens also using this kind of paradigm. And you'll see why, because it's pretty easy to do. So if I have a lot of tasks composed of processing lots of data that produce lots of other data, but in a very structured way, I keep applying the same kind of thing to the same kind of data and sort of put it together, it becomes very easy to use hundreds or even thousands of CPUs. But it has to be that I can structure the code to do that pretty easily, or I'm not going to bother with it. So MapReduce provides some very basic functions for the core structure, and then you can define user-defined functions that will go into the example, and we'll go through an example in a second. It does automatic parallelization distributing. It does most of the communication for you. It's extremely fault tolerant. If a machine goes down in the middle of it, you won't even know. It does all of the I/O scheduling and some level of status and monitoring, not fine-grained. So if I wanted to know the time and processing of every process, it's actually not good for that. It's not designed because it's designed to hide all that from you. But I can get high-level status and monitoring of what's going on. It is extremely widely used in research, not just in computer science, but in all kinds of other fields for bioinformatics, particle physics. Right here is a nice recent survey, a reasonably recent survey of its applications in computer science. So if you're looking at how does it get used in different research areas, including maybe yours, you can look at that research link and find out. So let's go through a really simple MapReduce operation and sort of see what it would look like. So if I wanted to do this, everything is broken down into code that lives in one of two things: map or reduce, which is why it's called MAPREDUCE. So map provides a function on individual data in a data set to create a new list of values. So if I think of map as literally a mapping function, a lambda function in Python or in Lisp, I have a function, may or may not have a name, but if I have the function square that takes in one item and squares that item, then the map would return, the map of square to the list 1, 2, 3, 4, 5, would return the list 1, 4, 5, 16, 25. Right? So map is literally an operator. It is in Lisp. It's an operator that applies a function over a list, and it returns a new list. Right? So it's the processing of the data. Reduce combines data in a list to create a new value. So if I have the reduce operator, say sum equals, it'll take each element in the array and it'll return the sum of them as I go plus equals. So if I do reduce of 1, 2, 3, 4, 5, I get 15, the sum of the elements. So if I wanted to do an operation over a very large set of data that squared every item and summed them all up, I could do it using these two functions, map and sum, and I could get the sum of the squares of a whole bunch of data. Okay? And that's it. If I can define my problem and I do my processing as map something over data and then reduce, okay? Reduce reduces everything it gets in its list to a value. It's not reduce the list to make it smaller. It's reduce it to a value. But if I map this over thousands of items, it's going to use the fact that I can break the item into a bunch of lists, reduce those, and then reduce those again. So if I do lots of operators, it'll satisfy that. If I have these two functions to do a MAPREDUCE inside of AWS, I would go in, I would set up my job name, in this case my job flow, set up this going to be streaming, which means I write in a step reduced manner and it's going to apply it to everything. I can also have my own custom jar or a pig program, which I'll show you an example in just a second about that as well. It asks me where's the input of the data. So in this case, I'm telling it where to get my data from my local file system. Where I want it output, notice the output is like a bucket. So that's my file system elements I'm going to put it. What is the map function? So in this case, this is an example with a word splitting program. And the reducer is aggregate, which is going to break everything up. And then you can pass in a couple of extra args. After that, I say, well, what's the max number of instances I want to have it run on? I can say 4. I can say 400. Right? If it doesn't need them all, it won't let that happen. I think if you need more than 20, you have to get permission. There's a slightly different interface you have to go through, but for up to 20 or so, it's very easy. And then I say how many instances. Instance pricing and everything is like it was before. After I've done that, it'll put it all together in my job flow, and it'll say it's starting, and I can watch it. And that's it. It is now running that process over many, many pieces of data. And I don't have to worry about how many processes it's using, where the data is coming from. So with a little bit of work to structure your problem as map and reduce, and the map function can actually be pretty simple. So if I was running something that is trying to, for example, do machine learning, map might take the list of data, right, and apply machine learning to it, right, and produce an answer, right? And then I can run a whole bunch of instances that do that, and reduce might be compute average performance. So if the code runs and it says, here's my accuracy, then reduce is, I've taken this big list of data and I've returned it as accuracy numbers, then I can get average accuracy really quick, right? Something like that. Reduce can actually, in a more advanced form, produce tuples, right? So it reduces things to one instance. But if that instance is a pair of numbers, that's allowed too. What it can't be is it doesn't change the size of the list. So it's got to do a dimensionality reduction. So if I have a very large list, I can get it down to 2 items. It'll be okay. So just to give you a feel, you can take almost any research you're doing and probably still get it. Some part of it is MAPREDUCE. Not that the research is inherently about MAPREDUCE, but if you can run an experiment, we talked about all these different designs, you might be running each of those experimental design elements in parallel and then using reduce as a way of combining the results to put them all together.